All right, yeah, thanks everyone. So we have a wonderful webinar today and very anxious to get started. Can you see my screen okay, Lucy?
Yes.
Okay, great. So if you don't know, Sierra Circuits is a Bay Area PCB assembler and PCB manufacturer. We specialize in military and high technology PCBs. And RF PCBs, which is a lot of what this webinar is about, and just high-speed PCBs as well. So if you haven't already requested a quote, I encourage you to do so. It'll help us fund these webinars. So in terms of what the topics are today, here's the title slide. As you can see, we're really going to dive into layout techniques. At least that's what my presentation is about, and then I'll hand it over to Brian. Okay. So what signal integrity challenges do you have in high-speed PCB designs? Well, so when PCBs are operating, at even frequencies beyond 10 gigahertz, several critical signal integrity challenges arise, such as impedance discontinuities, crosstalk, signal reflection, and even EMI. So when the decay isn't uniform across the board or is too high, it can lead to signal integrity issues. And so we're going to talk about material selection first. So high dielectric constants tend to increase the capacitive and inductive coupling between the traces. And this means that the traces start interacting more together, leading to crosstalk and noise. So you want to select a material with a higher dissipation factor. Sorry, selecting material with higher dissipation factor will increase the risk of signal attenuation. So you don't want to do that. Also, you have to be aware of the CTE of the copper and dielectric. If they don't match, you can have separation even after the build of the PCB. So in order to reduce the signal loss, you want to opt for materials with low dielectric constant. And some of the optimal performance for high-speed PCBs can be achieved with these materials below, like a Rogers 4350, an Itera, a Megtron. And these are great materials. You should talk to your fabricator about the cost of the materials and make sure it really meets your end use requirement. Also, you can opt for a hybrid stack up, which would be using less of the costly materials. Now, when you opt for a hybrid stack up, you can also introduce other manufacturing issues. Like when you are programming your drill machines, you want to make sure that you program it just right for the hybrid materials. When you program your plasma, you want to make sure you program it just right for the mixed materials. So although it will get you a less costly stack up, it could also introduce more complications in the manufacturing. So you have to talk to your manufacturer to make sure they can handle that type of construction. So here's an example of a high-speed stack up. So if you place your RF traces and components on the external layers, you can easily see, your outside layers. You can see that things are good. You can measure easier prior to solder mask. And I always encourage you to add a copper pour to reduce any kind of EMI issues appropriately with proper spacing. You definitely do not want to place two adjacent signal layers together. This will definitely increase signal interference. So you want to properly create your stack up in terms of placing your ground and power. If you can have ground as your second layer, layer one signal, second layer ground, all the better. And then you want to ensure proper spacing between your layers. And in manufacturing, Uh, we manufacture with cores and prepregs, so a core does not change its dielectric height after lamination. So a lot of customers put cores on the outer layer. So layer 1, 2 would be a core. And this ensures a consistent dielectric thickness throughout the length of the board and the length of the sheet that we use to manufacture. Also you can be very conscientious about component placement and how you separate the sensitive high-speed signals, RF signals from, let's say, power components. So what are the best strategies to achieve good controlled impedance? So in order to maintain signal integrity, you want to ensure consistent trace widths, which less copper, the better. So it's easier to etch, consistent thickness. Any variations in any of these parameters can lead to impedance discontinuities. And in general, a larger or thicker copper trace will help reduce impedance. And here's some strategies listed, how you want to route your traces. And then specifically, you want a nice solid ground pour, but if you have to route signals over two different, reference planes or, voltages, you need to incorporate stitching capacitors. And these capacitors provide a continuous return path for your high-speed signals. You also want to limit the number of vias in the high-speed signal paths because each via can introduce a small amount of impedance, and too many vias can disrupt the signal flow, causing reflections and loss. So, and then lastly, you're going to want to minimize the length of your high-speed signal traces if you can. Long traces will increase the risk of signal loss, delay, impedance mismatch, etc. So we have an impedance calculator on our website, and if you haven't been to our tools section of our website, please, I encourage you to check it out. Lots of powerful tools there. All right now are free. And so I think we're going to do a demo. Is that right?
Yes, Pranav.
Yes.
Okay, I'll stop sharing then.
Uh, Hello everyone. This is our impedance calculator tool. Uh, it's based on the 2D numerical solutions of Maxwell's equation, and so it renders a very accurate results for your engineering and manufacturing analysis. So on the mm, left hand side, you'll see the structure, different structure that we have available and the models. So we have uncoated microstrip, coated microstrip, embedded, and strip line. And we have different models such as single-ended differential pair. We have coplanar models as well as coplanar without ground models. So to choose, you need to select the required model and the structure, and you'll see the calculators which are available with in those categories. So we have a normal model, and then we also have a composite dielectric model where you'll have, if you have more than two dielectrics in between the trace and your reference, then you can go with the composite model, and you'll have a better result in those scenarios. So now click on open and the calculator will open. So let's move on to this calculator. So I opened a coated microstrip differential pair calculator. So here you'll see the image, how the geometry looks. Below you'll see the units selection drop down where you can choose between the empirical and metric system. By default it will be mils. Now for the demo purpose we'll keep it mils. You need to enter the dielectric information such as the dielectric height, dielectric constant. This is the coated geometry that I have selected. So the coating parameters are required, coating heights and the coating dielectric constant. Also you need to enter the trace information such as your trace weight, trace thickness, we have one parameter called delta W. This parameter is the trace is not of a rectangular shape. It takes a trapezoidal shape during manufacturing. So this delta W factor takes care of that, and we have this table here where there's a guideline of what delta W you should select. Actually, it is depends on the copper weight. So you can refer to this table while entering the delta W. So there are two calculations here. One is if you know the target impedance, you enter the target impedance, this target differential impedance, and you press calculate W. So this will calculate the trace width for that particular differential impedance, and it will show you. The other way is you can enter a trace width of your, say if I make 3.4 and I can press calculate ZD. So the forward calculation is also possible, wherein you enter the trace width and you can calculate the impedance. It also calculates and displays other parameters like coupling coefficient, odd and even mode impedances, propagation delay, and even the trace inductance, mutual inductance, and more parameters. So yeah. So this we also have other calculators along with the impedance like loss, crosstalk, etc. Uh, you can check it out on our website. Yeah. Thank you.
Yes, definitely check out our tools on our website. And um, definitely ask questions. I see a few questions coming in, and team, please, respond to those questions. Okay, I'll share my screen again. Can you see it okay? Oops.
Yes.
Okay. Okay, so we're going to talk about trace termination. So is it a good idea to terminate your high-speed traces? Yes, it is. So unterminated transmission lines can create an abrupt change in impedance leading to your signal reflections, which can cause jitter. So you don't want this type of interference with the original signal. So reflections can also result in oscillations between the source and the load, which is known as ringing. And when a reflected wave interferes with the original signal, it creates a voltage spike that exceeds the signal's intended maximum amplitude. So you can also have destructive interference as well, where the voltage will dip. So expert advice from Eric. When we interviewed Eric as well on the maximum trace length you can have without termination, he gave us this rule of thumb. So the rule of thumb is to make the trace length in inches roughly equal to the signal's rise time. And he gave an example. So there's lots of rules of thumbs. Here's one. But just be aware of your signal trace length. I think that's the main point. So we'll talk about some possible ways to terminate. So you want to do a series trace termination. So you can place your terminating resistors between the driver and the transmission line, and the resistor is placed as close to the driver's side as possible. And then there's a couple more rules of thumbs here for a series trace termination. There's also the parallel trace termination. So this involves placing a shunt resistor in parallel with the receiver, and this matching resistor absorbs all reflections at the far end of the transmission line. So you want to position the resistor close to the receiver for the best results. And then you can also connect the parallel resistor to the power supply or ground plane, depending on the IC's internal circuitry. So best practices to reduce crosstalk. If you can, ensure 3W to 5W spacing between adjacent signal traces, where W is the trace width. This spacing will help minimize capacitive and inductive coupling between neighboring traces. So you want to place your signal planes close to the ground planes, preferably one dielectric away. And this proximity provides a solid signal return path, reducing the noise and electromagnetic interference. Really, really critical and important there. So you want to also potentially route your traces perpendicular to each other on the adjacent layers. That would reduce crosstalk. And you want to avoid overlapping critical signals such as clock lines and data buses on adjacent planes. And you can also add guard traces next to critical signal lines. And of course, you can also, add, via stitching. So strategies to reduce propagation delay. So propagation delay occurs when the data signals and or clock signals arrive at different time intervals at the receiver. So you want to implement the same number of vias for each trace. You want to adjust trace length and spacing to ensure uniform impedance. And you want to incorporate serpentine traces and meandering to achieve the proper length matching. So using a Faraday cage also to shield RF components or sections may be useful. By enclosing these sensitive circuits, you can effectively block external EMI. And I also mentioned, ground core is your friend. You also want to incorporate conductive shields around sensitive circuits. These shields act as a barrier, blocking unwanted EM radiation. And then ensure that these shields are connected to the ground plane. You also want to create via fencing or via stitching by placing a network of vias above and below RF traces. For serpentine structures, ensure they are grounded through the top and bottom ground planes. And when you're working with microstrip lines, the situation is slightly different. Since the top side lacks a ground plane, connect the via fencing on the top layer using a trace. So here's some guidelines for doing proper grounding planes for your high-speed signal. So proper grounding is crucial. So you want to design a continuous ground plane with no breaks if you can. That's the best way to avoid your impedance discontinuities. So if you need to, you can also dedicate a ground plane for each critical RF signal layer. That would be the most ideal. And you can also implement via stitching along the edges of the ground plane or around RF traces, which we've talked about a couple times, but it's really key to achieving a good design. And so via to via spacing depends on the specific value of lambda. So typically the via to via gap should be between lambda by 20 and lambda by 10 to avoid overlapping and interference. And there's a couple more points here specifically for via stitching. Next, we're going to talk about decoupling capacitors for reducing the PDN noise. So when selecting your capacitors for filtering, always choose capacitors with self-resonant frequencies close to the frequency you need to filter. So remember, a capacitor's SRF is inversely proportional to its capacitance value. The lower the capacitance, the higher the SRF. So use multiple low inductance decoupling capacitors of the same value. This helps improve filtering of high frequency noise. Place these capacitors close to IC's power pins. Always mount the decoupling capacitors on the same layer as the components. This minimizes the parasitic inductance. And use individual ground vias for each capacitor. Ensure the same ground via isn't shared between two capacitors to avoid noise coupling. All extremely important points. So here's a few best practices for designing RF PCB layouts. You can route your RF traces first to help implement impedance matching techniques. Never place your RF trace in a normal trace in parallel. Place RF traces and components on external layers to achieve the uniform impedance. For shorter interconnections between components, use microstrip lines to route the RF signals. Use smaller vias, ideally with diameters between 8 and 12, to minimize parasitic inductance. Do not add test points on RF traces. This might cause impedance discontinuities. Avoid unwanted trace and via stubs to prevent signal attenuation. All great advice. So I think we have another demo, the via stub length calculator. So I'll pass it over.
Yeah. Uh, Hello. Yeah. So This is our maximum VR stub length calculator tool. So it computes the maximum VR stub length and its resonant frequency. So we all know that VR stub is a part of the VR that is not used in signal transmission, and it acts like a resonant circuit, and it stores a maximum energy at a resonant frequency. So the length of the VR stub should always be less than the acceptable or within the acceptable range, to avoid any signal integrity issues. To calculate VR stub length, you need to enter the dielectric constant, let's say 4, and you can enter any of these three parameters, which is the data transfer rate, fastest signal rise time, or maximum frequency content. So any one of these three parameters you can enter. So let's say I have a 10 Gbps signal, and press the calculate stub length button, and it will show you the maximum VR stub length that is possible. In reverse, we also have the reverse is also possible. We have one more tool. You can change to the next step. Here, if you enter a stub length, you can also see how much is the frequency for that stub length, which is possible. So, say I enter 4 as a dielectric constant. My VR stub length is 50 mils, and I can calculate, press this calculate button, and it will show me what is the maximum frequency content. So both ways you can do the calculation. Along with the frequency, it will calculate and show the your fastest rise time for that frequency, data transfer rate, and what is the resonant frequency for that VR stub. So yes, so yeah. Thank- yes. Over to you, Amit.
Okay, thanks. Let me see if I can share. Okay, can you see my screen?
Yes.
Okay, some DFM rules for the RF circuit boards. So start with drill the copper clearance that's 8 mils or more. For a 4 to 6 layer board, as your board gets higher in layer count, you want more drill to copper, because at lamination time, materials will move around. It's harder to drill. So if you have a 20 layer board with sublams, the more drill to copper you have, the better, because a lot of people will do a sublam and then they'll have a through via through the two subs. If the drill to copper is not good, then some fabricators will not be able to, build that construction. So drill to copper is a really key thing, and design tools don't check for those in the DRC. So it's important to check, ask your fabricator if they can do that. So for laser drilled holes, the minimum hole sizes before plating, roughly 4 to 5 mils. For through holes, either a 5.9 drill or 7.1. And then, you can always reference these rules later. So I'm not going to read them all. I'm looking forward to passing it over to Brian. So if you have any questions on any of the DFM rules, please type that in the chat. I do want to point out solder mask. A lot of people just give a solder mask 1-to-1, and if it's a standard board, that's fine. But if there's any learnings that you have from after assembling the board, you want to modify your solder mask and even modify your paste layer for any sensitive components or components that you're learning from after the assembly. So the whole process should feed back to your pad design, your solder mask design, and your stencil design. So a lot of times, we're just getting the same footprints over and over, and it's surprising that people aren't taking that feedback, from the assembler and making modifications to their pad stack. That's called continuous improvement. which is super important in what we do. So here's some fab notes that we would recommend to have on every board, including your high-speed RF boards. Now, we do get a lot of designs with missing information. So here we've just added a quick checklist so that when you submit your designs, you have something to reference prior to submitting as a double check. Anytime, we definitely do the check for you, but that will cause delays. So having a checklist on your end and following the checklist is really a good best practice. We're also releasing some more checklists that we've developed through the years. And as we release them, we'll let you know. But here's some of the checklists that we have today. And then, as always, we have a ton of resources on our website. They're all extremely well put together and well thought through by experts, both internally and externally to Sierra. So I definitely encourage you checking out our design guides. So I'm done with my portion. Now I'm going to hand it over to Brian.
All right. Thank you, Amit. That's a great presentation with lots of good information.
Thank you.
I actually was not aware of that of the VS stub calculator. I think that's a great tool, and it's something I think many people may overlook. I know that in our designs, our VNA designs, we use a lot of blind vias for that very reason. We can't tolerate the stubs and the resonances caused by that. Before
Brian, did you want to share your camera?
Yeah. I can do
Okay.
that. Hey, so I'll bring up my presentation in just a second. I just while I was listening to your presentation, it brought some thoughts to mind.
Sure.
That I think I might add. You had some you had the coplanar waveguide with ground calculator, well, a little bit microstrip and a lot of other things. But what came to mind is something that I've seen many times. People sometimes put a coplanar waveguide with ground stitching on a PC board, and then there'll be copper that just goes to the edge of the board and no more ground stitching. And what happens is the trace will actually excite the adjacent copper, and it will resonate wherever that's quarter wavelength or half wavelength long or something, and you'll get a huge ding in your signal amplitude. So if you do via stitching, ground stitching along your coplanar waveguides, also throw them into the ground plane around the trace all the way to the edge of the board. Otherwise, you will have problems.
Okay, that's great. I think those practical suggestions are exactly why people are here. So thank you.
Yeah. One other thing, also be aware, and you alluded to it in your presentation, be aware of the ground plane current, because if you're running a coplanar waveguide or a strip line or a microstrip, then RF is running along the trace, and we're all acutely aware of that. But there's also an RF current directly below it on the ground plane. So be aware of that current and where it has to go. And if you slash through it with a trace, then you're going to cause problems for that return current. Just one other thing too, the decoupling caps you mentioned, using like 2 or 3 of the same value. That's excellent advice. Steve Sandler at Picotest has written quite a bit on this. You can use 3 of the same value and you'll probably be fine. But you should also, if you can, verify the power plane impedance, and you can do that with a VNA. Picotest also sells probes that you can use with our VNAs. So you can use a 2-port VNA to make measurements of your signal plane down to milliohms, and you can see the effect of the turning on. You can measure a power plane and see that it has a low impedance. And when you turn it on, does the impedance stay flat, or do you see a peak? Because if you do see a peak, then your little point of load regulator could be unstable, and we see a lot of that going on. So So even though you follow the manufacturer's recommendations, you really do need to verify your power plane impedance, and you need to use a VNA of some kind to do that. If you don't, you're just looking for trouble, because the peaks in the impedance will lead to ringing and noise propagation throughout your circuit. Okay, with that, I will share my screen. And I'll start through my slides. So I'm just going to speak about the high-speed digital PCB design. I know we probably have some RF designers here too, and a lot of this is applicable. But I think there's, the digital speeds are getting higher and higher, and we have to be cognizant of the fact that now the digital designers are having to follow RF principles in their design. So, why do you need it? HDMI is evolving. I think it's at, 5 gigabits per second now, but it's evolving, all the way up to 48 gigabits per second in multiple lanes. But there are folks running 10 gigabits per second on a single lane, and even higher. I think I've heard 24, 26 gigabits per second on a lane, which is getting pretty crazy. USB-C will coexist with HDMI, but it's also evolving. USB 3.2 is going to be up to 20 gigabits per second. And all of this stuff has to be on a PC board at one point or another. In the automotive space, we have cameras and sensors all over our vehicles, and they're pumping data all over the place. So, each one of these little displays that we're running require 3.5 gigabit per second data rates. So we have to move mountains of sensor and video data, and all those go through circuit boards. So what are the implications on just throwing some numbers around? If you have 10 gigabit per second data rate, you probably need 100 picosecond bit width and 20 picosecond rise and fall times, which are very fast. And in practice, we do this with differential lines originating and terminating on a PC board. And a proper PC board design is crucial, and a VNA is required really for early prototype evaluation. And we're going to use differential data lines for this for the most part. Why do we do that? Well, there's the common mode noise immunity. There's less radiation into the air, and less susceptibility to noise as well. The digital lines are compared to each other and not to any fixed reference voltage, and that's pretty huge. So they can float on top of a DC offset if they need to, and they're not compared to perhaps a noisy reference voltage. So the bits are cleaner that way because they're compared to each other. Also, there's a constant current flow into the driving IC, since it's pushing both up and down simultaneously, which is a good thing. So how can I verify, my signal integrity of these differential lines? Well, if I have, many pairs like this, and I'm interested in measuring their differential insertion loss, return loss, the near end crosstalk, far end crosstalk, and that sort of thing, because the near end and far end crosstalk that you can measure with a VNA will at some point will end up being digital errors of one kind or another. So we can minimize these things in the RF world and see the benefits in the digital world. This, as we're showing here, is something that could be measured with a 16-port VNA. I have four lines, and I'm going to put one port on each line. Copper Mountain Technologies has a 16-port VNA. This is an 8-port VNA here, but we can load it up with another 8, and you could connect that to 4 differential lines and get all of your insertion losses, return losses, and crosstalk interactions between the pairs, and have all that information at a glance. So this is an essential piece of gear for measuring that kind, in that kind of situation. Also, time domain is huge for measuring the signal integrity on a board. Your signal is moving through the board. It might dive through a via, or it might go around corners, or it might go through a connector. And every one of those things can cause reflections. So we can evaluate those reflections. Of course, the amalgamation of all the reflections affects the overall return loss of your measurement. But in the time domain, we can see where those reflections are occurring. And we can see whether the connector is a problem, is the via the problem, is there something else going on? We can see where on the board the issue is. And we can do that with pretty amazing resolution. If you use a 43 gigahertz or 44 gigahertz VNA, and if the board supports that frequency, then the resolution is ridiculously small. You'll be able to see the problem between two pads on on a connector. So it's a very powerful method for looking at a circuit board and viewing the integrity. One other thing to mention here is, I showed this, and I could measure this with a 16-port VNA. Well, if you're just looking at a single pair and you want to look at it in the time domain, and one differential pair, you can connect port 1 to one side and port 2 to the other wire of your differential pair and look at it in the time domain, and you can see everything that's happening along that line. So a 2-port VNA is sufficient for a time domain measurement of a differential line. So what allows it is the built-in trace math function that's in our software. So if you're measuring it with a 2-port VNA, and take S11 plus S22 minus S21 minus S12 divided by 2, that is SDD11, or the differential return loss. So it's a pretty simple calculation to do. How do we go from our RF readings perhaps to an estimation of the different digital performance? And I'm not going to go into this into detail because I'm really not an expert, but I'll point you to where the information is. IEEE 802.3 outlines the channel operating margin. And I think the guys at Samtec really developed a lot of this. And if you go to their website, there's some example MATLAB code that will actually calculate the channel operating margin based on RF measurements. And it produces interim results for separating and budgeting channel impairments. Now, why would you need to do this? The reason why you need to do this is that you can make return loss measurements. I'll show one here shortly on the circuit board. And it might look pretty poor as you get way up in frequency. It might be 9 dB return loss, which sounds pretty bad. But with error correction, both forward and at the receiver, you can recover a lot of the performance in the digital domain. And there's something that's called effective return loss. So it may have an actual return loss of 9 dB, but it might have an effective return loss of 20 dB after error correction. And COM I think COM comes up with an answer for that. So that's something you might want to look into if you want to put a number to how good is your board design for digital. So here's what differential insertion loss and return loss might look like for an HDMI pair. This was an actual HDMI cable, and it's not terribly exciting. You can see that at about 500 megahertz it's falling apart pretty badly. But again, error correction can push that frequency response out quite a ways. Our VNA in this case is doing the unbalanced to balanced conversion. It's doing that calculation that I mentioned earlier. So it's subtracting unbalanced measurement, adding and subtracting unbalanced measurements to create the balanced version. So you get SDD11, SDD21, and so forth. How would I use this information? Well, you can look at a 3 meter length of RG174 cable, which is not really a very high frequency cable, and it has about 15.4 nanoseconds in this case. I measured it with a VNA, and you'll be able to see this. You can see on the very far right, there's an impulse response. That is simply the time domain response turned on our VNA, and you're measuring S21. And what you see there is actually the impulse response looking through the cable. So what can you do with an impulse response? You probably remember from your math days that if you convolve the impulse response with some function, then you're basically getting the result of what you would get if you put the function through the cable. So I created this little bit stream here of ones and zeros in the timing I just made up, and I convolved that digital data with the impulse response, which I took from the VNA from that cable. All I did was save the impulse response to a CSV file and did the convolution. And you can see that the convoluted bit stream on the bottom is what one would actually expect if I put that digital data stream through that cable. And you can see it's fairly poor. It's, some of the ones are not making it all the way up, and some of the zeros are not making it all the way down. So, I mean, there are ways to correct this, of course. I would mention just one more thing. That was the impulse response. The pulse response, if you look into COM, the pulse response is actually a single bit, a 1. So instead of using the impulse response, they use a single 1, and they use that to characterize the digital system. So it's clear that high-speed data is impaired by effects of cables and circuit boards and whatnot, and it can result in poor amplitude balance. And clearly you could do some digital pre-emphasis like I did here. I just push the ones up a little higher and the zeros down a little lower, and convolved once again, and you can see that the result's a little better. So the point here is that error correction can make a big difference. I'll just mention here that effective return loss was introduced by Rich Millets of Samtec, and it incorporates the equalization improvement to give you a figure of merit for your digital design. But a VNA measurement of the actual return loss is needed to evaluate this. So let's look at a real measurement. Have to switch. So now I am looking at, and I need to move some things out of the way. I'm looking at this circuit board, which Sierra Circuits kindly provided to me. It's a little hard to see, but here at the top there's a 100 ohm differential line, and it's very, very small traces. And I've hooked to the board using a little SMA semi-rigid pigtails, which hopefully you can see on my camera. And then I've just connected that to my 4 ports on my VNA. The VNA then is running, doing that calculation that I mentioned earlier, and you can see in the top trace here is my SDD21, that's my differential insertion loss through the line. And the pink trace here is the differential return loss, which is quite good. You can't really tell unless I change to that. Now you can see that the return loss of that line is better than 25 dB at low frequencies, and it does eventually tail off as you get to higher frequencies, as is to be expected. There's clearly some loss, about 4 dB at 4 gigs. Again, I think this is FR4, so that's to be expected as well. The return loss falls off, at high frequencies, but again, with digital error correction, we could probably use this, maybe up to 6 gigahertz, maybe a little higher. If you had to go higher, you would use just use a better material like a Rogers 4350, as mentioned before. I did mention time domain earlier, and so in this panel down here, I'm doing the characteristic impedance versus time or distance, if you will. I've actually de-embedded the probes that I have here. The de-embedding I did with our automatic fixture removal software, which is quite handy. So if you find yourself in a position where you have one of our VNAs and you have a lead in and lead out of some kind you need to remove, the automatic fixture removal software will simply measure it in a snap and then automatically de-embed it from your measurement. That's what I've done here. So what you're seeing, a little bump here at the beginning is simply probably my soldering to the pad, and there's a little bump on the output, same thing. The characteristic impedance is quite good. It's 99 point, or 98, 99 ohms. It's well within the accuracy of the for 100 ohms. I'm also measuring STD21, the impulse response that's looking through the cable. So we can basically see that the impulse response basically tells us how long the circuit is, and it's 969 picoseconds, almost a nanosecond. Some other things that I haven't shown here, but I could. This is a differential line, and many people are interested in line-to-line skew. So I can measure, instead of showing SDD21, I could show S21 and S43, and those would be the two traces separately. And I could measure the delay of the first trace, the delay of the second trace, subtract them to find the skew between the two of them in time. And that could be important because skew in a differential line leads to an effective differential to common mode conversion. And it ends up being causing an error, a small error in your digital data stream. It closes the eye somewhat, if you will. So this is a tool. This is the kind of tool you'll need if you need to measure and verify your circuit boards for high frequency performance, both for RF and for high speed digital cases. Copper Mountain Technologies has quite an extensive line of VNAs from 1.3 gigahertz on the very low end to 44 gigahertz in a standalone compact, and up to 330 gigahertz using our extenders. So we cover the whole gamut in the frequency range. You'll find our prices to be very competitive. And if you go to our website at www.coppermountaintech.com, we have a lot of resources that you might find very interesting. We have webinars like this one. We have technical papers written on many subjects having to do with VNA measurement and metrology, which you might find very useful. And now I'm thinking we're going to need to add some calculators since Sierra's done such a good job of that. But we have a lot of good resources on our website as well. So that's about it for my presentation. I want to thank you for the opportunity to speak to you, and hope you all have a great day. I'm sure we have questions.
Thank you so much, Brian. Let's do a quick poll before we start the Q&A, okay?
Yes.
And here we go. Okay, and I see we have a few questions in the Q&A section. Amit, are you ready?
I can answer the second one, which is, I think, directed to me. And actually, I do know the answer to the first one. SRF is series resonance, I believe. Yeah, okay. I'll let Amit answer that one. But on the second one, are you saying that the PDM impedance can be measured while the DUT is powered? Yes, as long as the voltage is less than 35 volts, our VNAs are protected from DC. So it is actually best to measure PDN impedance with the power supply powered, because you want to see, as you try to disturb the power plane with the VNA signal, you want to see what the regulator does with that, and is it stable?
Okay, and you can answer the first question as well about SRF.
I believe SRF series. Is that the series resonance? I hope that's what the answer is. You know, every capacitor will have some lead inductance, and at some point it's going to resonate with the capacitance. So, large capacitors end up having a lower series resonance, and small capacitors end up having a higher series resonance. After resonance, a capacitor is really not much of a capacitor anymore. It's more of an inductor. So knowing the series resonance is fairly important.
Okay, thank you. Yeah, I think we have more questions for you, Brian.
Okay. Yeah, I would just me jump in anytime you like, but I think I have most of this. Should the RF shield be connected directly to the PC board ground? Yes. Yeah, I mean, I've always the way we design our boards, we have many shields, and we do have we do connect it directly to ground plane. I see that Amit wants to say something here.
Oh, no, it's me clicking the answer live button.
Oh, okay, all right. The trace length for the demo board, it is about 8 inches, maybe a little less. So it's so it's FR4, and the dielectric is about 4.5. So you could figure it out from there pretty quickly. The velocity on the PC board is going to be C divided by the square root of 4.5.
Okay, someone is asking if you can show the measurement setup. Is that possible?
Yeah. So I have camera's not terribly close, but I have 2 traces on the circuit board up along the top here. I have these little SMA to open pigtails, and they're semi-rigid, and I got these from I know it's slipping my mind, but they're connected actually to the ends of the traces. So I have port 1 connected on one side, port 2 connected to the same trace on the other side, port 3 is connected to the other trace, and port 4 is connected on the other side of that same trace. So I have 4 ports connected to the 4 ends of the lines. That's my test setup. That's all there really is to it. This equipment cannot show eye diagrams. There is equipment that will do that, but with the VNA, not really. It could be done, but there's be a lot of fakery involved in order to do it, because you'd really be measuring in the frequency domain, and then you'd have to put the harmonics together to generate a virtual square wave, and then plot that to create an eye diagram, and then add fake jitter. Really, at the end of the day, you're kind of better off using an actual digital setup to do that. Yeah, the physical connection between the VNA and the circuit board. Well, I was afraid of actually breaking my tiny little connectors. I think you can probably see it a little better now. So I have the four cables, the 4 connectors. Oh, these little pigtails I got from a distributor called RFMW. And they have these, and I made sure that these were good to 18 gigahertz, because I wanted to be able to get a good high frequency measurement. I de-embedded them all the way up to 18 gigahertz using our software. Oh, when you measure the skew with the differential pair, that's a good point because the differential pair itself may not have a reference ground. In this case, the board has a ground plane, so I'm simply using the ground plane on each side. Although the differential pair doesn't really need a ground plane. But it does actually have some capacitive coupling to the ground plane, so it does to some extent determine the impedance of the differential pair. If you're looking at a cable with just wires, differential twisted pair, for instance, in that case, you need to have like you put a copper plate underneath the entire test setup, and all it does is serve as the common ground for the VNA. Yeah, when measuring the PDN impedance with VNA, the location of port 1 and 2 matter. Where should the ports be located? That's a great question. When you're doing low impedance measurements of a for PDN, you're measuring maybe in the milliohms. What you're doing is you're putting the two ports together. Ports 1 and 2 are actually connected directly together, and their grounds are connected together. And you are measuring, you're doing an S21 measurement with the PDN going to ground between the two. Why do you do that? Because that's the only way you can get an accurate, very low resistance measurement. Measurements from about 1 milliohm to 20 ohms are done with S21 and with the DUT going to ground between them. Measurements from 20 to about 200 ohms are done straight through the DUT with a 1-port measurement. And from 200 ohms up to about a megohm, you put the DUT in a series and do an S21 measurement through it. That's how you measure resistances from all the way from a milliohm up to a megohm using a VNA. But for PDN, you're doing what's called a shunt through measurement, I think it's called, and you're doing an S21 measurement with the DUT to ground in between. Now, again, Picotest has little probes that you can just hook the cables to, ports 1 and 2. And it has a single probe which is connected to both ports and a ground, and you would just touch it to your PDN and ground, to your power and ground, and you make your measurement with that. So you might have a look at that. Yeah, I'm not sure which ones. Go to their website. They have a number of them. Your choices are going to be the pitch between the hot part and the ground. They're all pretty much made the same way, though. Yeah, what's the value of doing the VNA measurements for high-speed digital interconnects? Well, simulation can be done before manufacturing. If you have the full simulation information, you might be good to go. I mean, some of the manufacturers like Molex, Santec, and some of these other folks will give you all the information that you could plug into a simulator like ADS or one of the others, and doing that, you could do a pretty darn good simulation. But there are other effects. I mean, because the connector alone has its own effects, and then you put it on a circuit board, and then you have effects between the pads and the grounds, and then you have pad-to-pad interactions. So at the end of the day, it's a pretty good idea to actually make a measurement if you can. And I should say some models do incorporate all of that as well, but I don't know. I'm kind of an experimentalist, so I like actually seeing the actual results. Yep. And yes, there will be a recording of this being made available. Yeah. How do you break the ground loop between the two ports, the PDN and the VNA? Another great question. That is done with a common mode inductor. I didn't mention it, but you can also get that along with the probes from the same source. And it separates that ground loop out. Normally, you don't see that if you're It depends on how low you're going. If you're going all the way down to a hertz, well, then our VNAs don't go quite that low. Then you certainly need that for the really low frequencies. If you're starting at 9 kilohertz, which is the bottom of our VNAs, you may not see that ground loop, so it might not be a big issue.
Okay, great. Did we answer the other questions? The table providing the max loss.
Oh, there probably is. It's probably in the IEEE spec for it, or the IEEE. ANSI, I think it's ANSI. I'm not sure who created these specs, but it'll be in the spec. I don't know it off the top of my head.
Okay, and there's someone asking if you can one set up test points ports on a populated board to measure SDD parameters?
You can, yeah, you can, but as Amit mentioned before, test points are a bit problematic. They're little capacitors to ground. If you put little circles or something that you can get to easily, they're going to be little capacitors to ground, and then they will cause reflections, and they'll, you know, they'll damage your digital response somewhat. But you can do it if you make them really small. And the little probes, if you get these little probes, they're very sharp, so you don't need much. Need much to get at them. So you know, anywhere you can get this little cleared copper, you can get a measurement.
And just below, someone is asking a question about the picotest probes.
Yeah, yeah. Check the website. Talk to Steve Sandler. He'll be happy to tell you.
Okay, 2 more questions.
Keep out on a pair of differential vias from adjacent copper. Well, any encroaching copper from to the sides of the differential pair will create a common mode impedance, if you will, or was it even mode? Yeah, yeah, it increases the even mode impedance of the 2 wires. So that factors into the final impedance. So as you encroach more closer and closer, you to some extent you kind of ruin the nice things you get from a differential line, and you lower the impedance of the differential pair. So it's not advisable to have the ground too close, but then on the same, you know, also you would like to have a ground between 2 differential pairs so that they don't talk to each other. When I did the de-embedding, did I use the S-parameter file from the manufacturer? I'll start with the VNA. This is the SN 5090 5090-8. So it's the 8 port. There's also SN 5090-16. So you can get this in all the way from 6 ports to 16. We also sell 4-port VNAs and 2-port VNAs, different models, different frequencies. You know, did I use the S parameters from the manufacturer for de-embedding? No, what I actually did was I used my 18 gigahertz 2-port VNA, which is in the other room. I connected to the probe. I connected to the pigtail from the analyzer. I shorted the end of the pigtail with some copper tape, and then I ran our automatic fixture removal software, which is able to generate a full 2-port S parameters for the pigtail from a one-sided measurement where the other side is grounded or open. I can't have it open because I actually had it soldered to the board. But it makes a single-sided measurement, generates the 2-port S parameters for the pigtail, and then I use that for de-embedding. And how does it get the 2-port S parameters from a one-sided measurement? There's a paper written by Doug Ritting, R-Y-T-T-I-N-G, on that very subject.
Okay, well, thank you so much, Brian.
My pleasure.
Thank you so much for doing this webinar with us. Thank you, Amit, for presenting. Thank you, Pranav, for the demos. Thank you to everybody who joined. And have a good day. I will send you the slides and recording this afternoon. Thank you, everyone. Bye-bye.
Thank you, Lucy. Amit, rest of your team. Great to meet you.
Bye everyone.